Okay, I'm going to go through the answers here for the 11.1 quick check. So the first question on here is just talking about the standard pressure and standard temperature. And these are numbers that you should just kind of know. Okay, so the idea is that 1 atmosphere is the same as 760 millimeters of mercury, same 760 torr, named after Torricelli, and that's 14.7 psi and 101.3 kPas. Now those numbers will actually be on the test for you, but it's kind of nice to have them in your head, then you don't have to look them up all the time. The other thing for standard temperature is at 0 degrees Celsius, which is 273 Kelvin. And remember, as we do problems in this unit, be sure and change your temperatures to Kelvin all the time. It's going to be very important. Okay, we need to be able to convert things back and forth. So the first thing, to go from Celsius to Kelvin, we just add 273. And I always try to remember, that Kelvin, is higher in the alphabet than Celsius. So if I want to go from Celsius, I have to add 273. And if I want to go from Kelvin back to Celsius, I have to subtract 273. And that's how I remember it. So negative 40 plus 273, I get 233 Kelvin. Okay, go milliliters to liters. That's just the metric system. And I'm going to use this conversion. I know that there's 1,000 milliliters in a liter. So when I multiply, I get 0.085 liters. If I do this, I would just kind of move this, I can just move the decimal point over 3 places when I'm doing a problem. Okay, atmospheres to millimeters of mercury. Now I have to use 2 numbers from my list of, standard pressures. And so, put atmospheres on the bottom, so that cancels. And then I get millimeters mercury on top. So 1.3 times 760, I get 988 millimeters of mercury. Okay, same thing here. If I want to go from PSI to kPas, okay, again, I need to pick out 2 numbers from my list. So the 14.7 PSI goes on the bottom, 101.3 kPas goes on top. So the PSIs cancel, and I'm left with 65.465 kPas. Since I had 2 significant figures here, I round that off to 65 kPas. 99.4 kilopascals to torr. Okay, again, I make a conversion using 2 of my numbers, kPas in the bottom, so they cancel. Torr on top, 760 torr, 101.3 kPas. So I get a value of 745.7. 3 significant figures, round that off to 746 torr. And the last, back from milliliters back to milliliters. Okay, again, using my metric system, I know that a liter is 1,000 milliliters, and I just have to multiply by 1,000, which means move my decimal point 3 places, so I get 0.40 liters. 2 significant figures, 2 significant figures. Okay, next problem is Dalton's Law, and this is talking about a mixture of gases. So if I had 3 different gases together in the same container, okay, and then together all those gases cause a pressure of 0.3 atmospheres. And this is my little pressure gauge up here. So the idea is every gas causes the same amount of pressure. So if I have, a mixture altogether of 0.72 moles, then for my nitrogen, if I'm saying that I have 0.24 moles of nitrogen out of 0.72 moles total of gas, then the pressure due to the nitrogen will be proportional. So if I'm saying, 0.24 over 0.72, that's 1/3. So if 1/3 of the gas is nitrogen, then 1/3 of the pressure is going to be due to nitrogen. Now, if I just officially work this out, I'm going to cross multiply. So I have 0.24 and 3.0. Cross this way, partial pressure in 0.9 and 0.72. Solve for the partial pressure. So 0.24 over 0.72 is 1/3. 1/3 of 3 is 1 atmosphere. This little guy here is officially called the mole fraction. Moles of nitrogen over the total moles. So you might see that written that way. Okay, the last problem on here has to do with Graham's law, and we know that the particles, all can cause the same pressure because the lightweight particles are moving very fast, okay, and heavier particles are moving more slowly. And here we can see, we have helium, and helium we know that weighs 4, and we have methane, and that weighs 16. So we say, well, who is moving faster? Well, then obviously the helium is going to be moving faster. Now the question is, how much faster does it move? Well, you say it's 4 to 16, so you might want to say that that's going to be, it's 4 times lighter, so it's moving 4 times faster. That's not true. Okay, the idea is that it's the square root of their masses is how you have to calculate the velocity ratio, and so it's going to be the square root of 16 over 4, which is the square root of 4, which is 2. So helium is faster, that part's easy, and it's not faster 4 times, it's faster by square root of 4, it's faster by 2 times. So helium moves twice as fast as methane, and that is the quick check.